The flatness problem is one of the most intriguing puzzles in cosmology. It asks a deceptively simple question: why is the geometry of our universe so incredibly close to being perfectly flat, neither positively curved like a sphere nor negatively curved like a saddle? Given how the universe has expanded over billions of years, even the tiniest deviation from flatness in its early stages should have dramatically increased or decreased by now. Yet precision measurements tell us it remains astonishingly flat today. Let us understand what flat means here. In general relativity, the shape of the universe is governed by its energy content. If the total density of matter and energy equals a critical value, the universe is flat, meaning Euclidean geometry holds on cosmic scales. Parallel lines never meet, triangles have angles summing to 180°, and the expansion of space is finely balanced. If the actual density is higher, gravity eventually halts expansion and causes collapse, a closed universe. If it's lower, the universe expands forever with increasing speed, an open universe. The problem is this: flatness is an unstable point, like trying to balance a pencil on its tip. Any small deviation from perfect density would amplify over time, either collapsing too soon or expanding too rapidly to form galaxies and stars. But that did not happen. Observations from the cosmic microwave background, CMB, especially those by the Planck satellite, show that the universe is flat to within 0.5% accuracy. If the early universe had even a 1 part in 10 to the power of 15 deviation from flatness, the curvature today would be vastly different. This raises the question: why was the universe so precisely tuned at the beginning? Is this a cosmic coincidence? Or is there a mechanism that forced it into flatness? The leading explanation is cosmic inflation, a brief period of exponential expansion that occurred just a fraction of a second after the Big Bang. During this phase, the universe expanded faster than the speed of light, smoothing out any initial irregularities and stretching space so uniformly that any curvature became negligible. Think of inflating a balloon. The more it expands, the flatter a small patch on its surface becomes. This is what inflation is thought to have done on a cosmic scale, but inflation itself raises further questions: what triggered it, and why did it stop? Could there be alternative ideas? Some physicists explore quantum cosmology, where the flatness might be a natural consequence of the quantum state of the early universe. Others entertain anthropic reasoning that perhaps only a flat universe permits complex structures in life, and we happen to observe such a universe because otherwise we would not be here to ask the question. Still others question whether our measurements truly rule out subtle curvature on ultra-large scales. So ask yourself, is the universe flat by necessity, design, or just luck? That is still an open question. What is clear is that our existence, galaxies, stars, planets, and life, depends on this near-perfect balance. If the universe were even slightly more or less dense in its earliest moments, it might have either collapsed within seconds or become a cold, structureless void. The flatness problem reminds us how finely tuned the cosmos appears to be and how much remains to be understood about its first microseconds. Would you like a visual explanation of how curvature works in cosmology, or a simulation showing how small differences in early density evolve over billions of years? The shape of the universe depends on its overall energy density and follows the equations of general relativity. A flat universe means that parallel light rays remain parallel over cosmic distances, implying zero spatial curvature. If the energy density were even slightly greater or lesser than the critical density, the universe would have curved, either closing in on itself, positive curvature. Observations from the cosmic microwave background, CMB, and baryon acoustic oscillations confirm that space is flat to within a 0.4% margin of error. However, early universe models suggest that even tiny deviations from flatness would have grown dramatically over 13.8 billion years. This raises the question: why is the universe still so flat today? Data from the Planck satellite shows the angle between distant cosmic structures aligns with a flat Euclidean geometry. It's like balancing a pencil on its tip for billions of years without it tipping over. It seems unnaturally precise unless something held it in place. The flatness of the universe is extremely sensitive to initial energy density conditions at the time of the Big Bang. A deviation of just 1 part in 1050 would have led to a completely different cosmic fate, either rapid collapse or runaway expansion. This extreme sensitivity suggests some form of fine-tuning in the initial state of the universe. If flatness was not baked in at the beginning, we should see a curved universe today, which we do not. This presents a philosophical and scientific problem known as the fine-tuning issue. Why did the universe start out with such an unbelievably precise energy balance? Without this fine-tuning, the universe could have collapsed into a black hole or expanded so fast that galaxies never formed. It's like aiming a rocket at the moon and hitting it dead center from Earth. Without a guidance system, it seems improbably lucky. The prevailing explanation for the flatness problem is cosmic inflation, a brief period of exponential expansion just after the Big Bang. During inflation, space stretched so rapidly that any initial curvature would have been flattened, much like how a balloon surface appears flatter as it inflates. This mechanism provides a natural explanation for why today's universe appears flat, homogeneous, and isotropic. Inflation also solves related cosmological puzzles like the horizon and monopole problems. Quantum field fluctuations during inflation later seeded galaxy formation, linking microscopic physics with large-scale structure. The observable universe may be only a small patch of a much larger, potentially curved cosmos that was flattened by inflation. Inflation is like stretching out a wrinkled bedsheet so taut that any bumps disappear, leaving a flat surface. The cosmic microwave background provides a snapshot of the early universe and encodes information about spatial curvature. By analyzing the angular size of acoustic peaks in the CMB, cosmologists can deduce the overall geometry of the universe. Measurements from WMAP and Planck show that these peaks align with predictions from a flat universe. If the universe were curved, the apparent size of these features would appear smaller or larger due to lensing effects. This high-precision data narrows the curvature parameter, U_k, to near zero. Despite observational confidence, the flatness still appears unnaturally too perfect without inflation. The first acoustic peak in the CMB power spectrum is located at an angle of tilde 1 dg, consistent with a flat geometry. It's like hearing a perfectly tuned musical note that could only result from a precisely constructed instrument. Though inflation is widely accepted, alternative theories challenge its assumptions or propose different explanations for flatness. Some quantum gravity models suggest that flatness could emerge from deeper symmetry principles in the fabric of space-time. Loop quantum cosmology and string theory explore these ideas but lack testable predictions so far. Another proposal is the cyclic universe, where each cosmic cycle resets geometry, but this too lacks direct evidence. Furthermore, the extreme fine-tuning required before inflation still troubles many physicists. As a result, the flatness problem remains a driver of deeper questions in cosmology. Ekpyrotic models propose that the universe came from a collision between branes in higher dimensional space, which may flatten geometry. It's like asking whether a perfect circle was drawn freehand or with a compass. We still debate whether the precision is accidental or engineered. Inflationary theory leads naturally to the idea of a multiverse, many universes inflating from different quantum fluctuations. In such a multiverse, flat universes could be common, and we just happen to live in one because only flat or nearly flat universes support complex structures and observers. This is the anthropic argument. We observe flatness because life requires it. However, this explanation shifts the question from physics to probability and selection bias. While consistent with data, the multiverse idea is currently untestable, raising concerns about falsifiability. Still, it remains a leading idea in theoretical cosmology. String theory landscapes predict 10 to the power of 500 possible vacuum states, many of which could lead to flat universe bubbles like ours. If you're in a hotel with 1,000 rooms and only a few have air conditioning, you're likely to be found in one of those few because you're alive to talk about it. It is important to distinguish between spatial curvature and space-time curvature. Even in a flat universe, space-time can still curve due to mass and energy content, as described by Einstein's field equations. Flatness refers only to the geometry of space at a given moment, not how it evolves or warps in time. Dark energy, for example, causes an accelerated expansion without altering spatial flatness. This distinction helps explain why gravity and expansion can coexist in a seemingly flat cosmos. Thus, local gravitational effects and global curvature are not the same concept. The bending of light around galaxies demonstrates local spacetime curvature in an otherwise globally flat universe. Think of a large flat sheet being dimpled in places where marbles rest. The overall sheet is flat, but locally curved by each marble. A flatness problem exemplifies a broader issue in modern cosmology, apparent fine-tuning of physical constants and conditions. Along with the cosmological constant problem and baryon asymmetry, flatness pushes scientists to seek a more fundamental theory. Such a theory may unify quantum mechanics and gravity or reveal new symmetry constraints on initial conditions. Until then, our understanding remains incomplete, even if models like inflation patch the problem. This invites philosophical reflection about the limits of current physics and the nature of cosmological initial conditions. The energy density needed to produce today's flatness had to differ from the critical value by less than 1 part in 1060 at 1 second after the Big Bang. It's like building a house of cards in a wind tunnel and wondering how it stood up without any glue. The flatness problem is not just about geometry, it touches on the origin of the cosmos, the nature of time, and the limits of observable reality. While inflation provides a plausible answer, the extreme precision required still suggests deeper underlying physics may be missing. Some researchers argue that the question itself may be misframed due to anthropic reasoning or quantum cosmology effects. Others see it as a doorway to new paradigms in fundamental physics. For now, the remarkable flatness of our universe remains one of the most profound and provocative puzzles in cosmology. Even with new telescopes and data, no direct observation has yet contradicted the assumption of flatness, making it both secure and puzzling. It's like waking up every day to find your messy desk perfectly organized, something you didn't do, yet it stays that way.